Good morning, students. Today we will discuss Lindeloff theorem. And in order to discuss this theorem, firstly, we discuss some basic definitions, which we already discussed in fourth section, compactness. So the first definition is, what is open cover for a topological space X? Let us take a topological space X tau, then a collection E of open subsets of X that is said to be open cover for the set X if X can be written as the union of A, where A belongs to this collection E. It means X is covered by the union of the members from this collection of open subsets of X. Then we say that this collection E is an open cover for the set X. Next we define subcover. Subcover means a subcollection E star of the open cover E, such that X is covered by the union of the members from this subcollection. So E star, which is a subcollection of open cover E, that is said to be subcover if X can be written as union of A star, where these members A star, they belongs to E star. E star is the subcollection of open cover E. Now, next to define Lindeloff space. A topological space X tau is said to be Lindeloff space if every open cover of X has countable subcover. Now, we will discuss Lindeloff theorem. In order to discuss this theorem, firstly, let us discuss a lemma, which states that if X is a second axiom space, then every open cover of a set G, which is open subset of X, has countable subcover. It means if we have a collection E, the collection of GIs, where these GI are open sets and G is the union of these GIs, means the collection E is open cover of G. Then we are to show that this open cover has countable subcover. It means there exists a countable subcollection E star of the collection E, such that G can be written as the union of members from this subcollection. Now, in order to prove this, because we are given that X is second countable space, so by definition of second countable space, there will exist a countable base for the topology of X. Or we can say that there exists a countable base for open sets. So let us take that countable base, that is beta, which is the collection of the members A n. Here n varies from 1 to infinity. Now, because G is the union of GIs, where I belongs to index set, so if we take X belongs to G, then from here we can say that X belongs to GI for some I. Now, because beta is the base for the topology and this GI, they are open, therefore by definition of base, there exists some member from beta such that X belongs to that member and that is contained in GI. Such members we have denoted by the sets A and X. So we get X belongs to A and X, which is contained in Gi. Now, let us take beta star be the collection of all such ANX which satisfy this equation. Then, beta star being a subcollection of beta that is countable. So, we can say that beta star is countable. Now, from the equations 1 and 2, G can be written as union of ANX, where these ANX they belongs to beta star. Now, let us use axiom of choice. So, by axiom of choice, for each ANX belonging to beta star, we can choose a member Gi from the collection E such that ANX is contained in Gi. And this is possible from here because here we can see that ANX that is contained in Gi. Now, let us take E star is the collection of all such Gi's which satisfy this condition. ANX is contained in Gi. Then we can say that E star that is a subcollection of the collection E, and because beta star is countable, so this collection E star that is countable. And from the equations 3 and 4, we can see that G can be written as union of A, where A belongs to E star. So this completes the proof of the lemma. Now, we discuss Lindeloff theorem. According to this theorem, in a second axiom space, every open cover reduces to countable subcover. It means if X is a second axiom space, then X is Lindeloff space. In order to prove this theorem, in the above lemma, replace the set G by the set X. So, this will complete the proof of Lindeloff theorem. Now, let us discuss a result based on this theorem. Every subspace of second axiom space is Lindeloff space. So, let us take a topological space X tau, which is second axiom space, and Y with the subspace topology tau Y, that is a subspace of the topological space X tau. Now, in the second axiom spaces, hereditary property holds. It means every subspace of a second axiom space is second axiom, and therefore we can say that Y with the topology tau Y, that is a second axiom space. Now we can use Lindeloff theorem. According to Lindeloff theorem, every second axiom space is Lindeloff space, and therefore we can say that Y with topology tau Y, that is a Lindeloff space. So this proves that every subspace of second axiom space is Lindeloff. Now, next theorem is, let X be a second countable space and beta dash, that is a base for topology, means base for open sets. Then we have to prove that there exists a countable subcollection beta star of beta dash, which is also a base for open sets. Now, X is second axiom space and beta dash, by definition of second axiom space, there exists a countable base for open sets. So we have taken beta dash as the countable base for the open sets. We have denoted this collection by the collection of members An, where n varies from 1 to infinity. Now this An belongs to beta dash, and beta dash is a base for the topology. So by definition, beta dash is a subcollection of topology tau. So every member which belongs to beta dash, that will also be a member of tau. So An belonging to beta dash implies that these an are the members of the topology tau. Now, because an belongs to tau, beta dash is base for topology. So, by definition, every tau open set can be written as union of some members of beta. So, beta means base. So, an can be written as the union of some members from beta n, where beta n that is a sub collection of the base. Now we can use Lindeloff theorem. So by Lindeloff theorem, because the space is second axiom, so that is Lindeloff space, it means every open cover will be reducible to countable subcover. So we can say that there will exist a countable subcollection beta n star of this collection beta n such that an can be written as union of the members from this subcollection. Now let us take beta star, that is a union of such subcollections beta n star. Then this beta star, that is a countable subcollection of beta dash. Now we claim that this beta star, that is a base for the open sets, means that is a base for the topology of X. Topology of X is tau. To prove this is base for topology tau, let us take G belongs to tau. Now, because beta dash is base, therefore by definition, every tau open set can be written as union of some members of base. So G can be written as union of some members of beta dash. So we can say that G is union of some members of beta n. And from the equation 1, we can say that G is union of members from beta n star. So from equation 2, we can say that G is union of some members from beta star. So we have proved that every tau open set G can be expressed as union of some members of beta star. So by definition, we can say that beta star, that is a base for open sets. So this completes the proof of the theorem that if X is second countable space, then for a given base for topology, there exists a countable subcollection of the base, which is also a base.